Buckle up, because today we're diving headfirst into the mind-blowing world of quantum physics.
It's going to be a wild ride.
We're cracking open quantum, Einstein, Bohr, and the great debate about the nature of reality by Manjit Kumar.
Fascinating book.
And it's not just a history lesson.
Oh, no.
We're going deep into the nitty-gritty of those earth-shattering discoveries.
The ones that completely transformed how we understand everything.
Oh, and what I find so fascinating
Yeah, tell me.
is how this revolution in physics,
It really was revolutionary, wasn't it?
it didn't start with some big dramatic breakthrough.
Not at all.
It started with what seemed like a tiny little problem.
A pesky little puzzle.
Kumar sets the scene beautifully.
He does a great job setting the stage, doesn't he?
It was the late 19th century, and scientists were feeling pretty darn smug about physics.
They really were. They thought they'd pretty much figured it all out.
Like just a few more tweaks here and
A
there.
little more fine-tuning.
Just a few more decimal places in our calculations, and we'll have the universe all figured out.
Exactly. Confidence is good, but maybe they were a tad overconfident.
A tad. But then along comes this thing called blackbody radiation.
Basically, how the color of an object changes as it heats up.
It's like when a blacksmith heats iron and it glows red.
Exactly. Or even something as simple as an electric stovetop.
It turns red hot when you crank up the heat.
It's something that potters have known for centuries, right?
Seeing those colors change as they fire clay in a kiln.
Exactly. They knew about it long before physicists figured out the theory behind it.
It's amazing how often practical knowledge gets a head start.
Hands-on experience can really get you ahead of the game.
But here's the thing about this blackbody radiation. It wasn't just a matter of fine-tuning those equations.
This was a sign that something big was missing.
Something fundamental in our understanding of how the universe works.
A missing piece of the cosmic puzzle.
And trying to solve that puzzle
This is where things get really interesting.
led to one of the most significant upheavals in the history of physics.
Enter Max Planck.
And this is where it gets kind of funny.
Oh, tell me.
Because Planck, at this point, he
Yeah.
wasn't even sure he believed in atoms.
Can you imagine that? A physicist who wasn't sold on atoms.
It sounds crazy now.
Right. Atoms are like physics 101 these days.
Exactly. But that's how revolutionary these ideas were.
They were challenging the very foundation of what people thought they knew.
So Planck's wrestling with this blackbody radiation problem.
Yeah.
He's determined to find an equation that explains it.
He's crunching numbers, testing theories, really trying to make it all fit.
And the only way he could make the math work was to imagine energy as coming in these little packets.
Like tiny little bundles of energy.
He called them quanta.
Quanta.
Yes.
Such a small word for such a revolutionary idea.
Right. And it's almost comical.
It really is.
Planck stumbles onto this groundbreaking idea, a concept that would completely upend physics.
Completely transform our understanding of how energy works.
And he wasn't even sure he bought it himself at first.
That's the amazing thing about science sometimes.
What do you mean?
The most unexpected discoveries come when you're trying to figure out something else entirely.
They're like happy accidents.
In a way, yeah. Like you stumble through a door you didn't even know was there and discover a whole new room.
That's a great way to put it.
And in this case, Planck stumbled into the quantum realm.
And once that door was open,
Once those floodgates were open,
there was no going back.
so we've got energy all chopped up into these little quanta. But where does light fit into all of this?
Because light, it's a wave, right?
Well, that's where things get even more interesting,
Okay, I'm intrigued.
because that's where a young Albert Einstein enters the picture.
No way. Even before the whole theory of relativity.
Even before he became, Einstein, he was just this unknown patent clerk at the time.
I love that he was already shaking things up even back then.
He was a rebel with a cause. So Einstein takes Planck's idea, this idea that energy is quantized, and he makes a daring leap.
Okay, what kind of leap?
He proposes that light itself
Yeah.
is made up of these quanta, what we now call photons.
Hold on. Light, which is a wave,
Right?
is now a particle.
It was a wild idea.
It's like saying that the ocean is made of tiny little droplets.
I can only imagine how the physics community reacted to that.
It must have blown their minds.
Light as a wave was a cornerstone of classical physics. And here comes Einstein saying, nope, it can be a particle too.
Talk about rocking the boat. But Einstein,
He was never afraid to challenge the status quo, was he?
he doubled down and insisted that light could be both a wave and a particle.
Depending on how you look at it.
He was a visionary.
He really was.
And you know what's even more incredible?
What's that?
He was right. This wasn't just some outlandish theory that he cooked up Einstein was working on something completely different,
Yeah.
this thing called Brownian motion.
I've heard of that.
And his work on Brownian motion actually helped to prove his point about light.
How so?
So imagine you're looking through a microscope at these tiny particles suspended in a fluid like dust and water.
Gotcha.
And these particles are just jittering around, moving randomly.
You've seen that under a microscope.
Looks like they're doing a little dance, right?
A microscopic dance party.
Einstein figured out that this seemingly random dance was actually caused by something bumping into the particles constantly.
Okay, we couldn't see.
And that's some
But
atoms. So he was essentially proving the existence of atoms, which were still controversial back then. It was a huge deal. He was proving that atoms were real while simultaneously arguing that light, something everyone thought was a wave, could also act like a particle.
Talk about a double whammy.
Einstein was already changing the face of physics, and he was just getting started.
He was a force of nature. But what's really mind-blowing is how all of this set the stage for a complete reimagining of the atom itself.
That's what's so amazing about this whole story.
It's like each discovery led to an even bigger question, an even deeper mystery.
It's like peeling back the layers of an onion.
And every layer you peel back makes you cry a little, because the universe gets a little bit stranger. It's amazing when you think about it.
What's that?
How this tiny little particle, the atom...
The building block of everything.
Exactly. How our whole understanding of it had to be completely revamped.
We basically had to hit the reset button on atomic theory.
Pretty much. And it all started with those quantum pioneers we were just talking about.
Planck with his energy quanta and Einstein with his light quanta.
They really shook things up.
They set the stage for a complete reimagining of what an atom even is.
And it's a good thing they did. Because the old model...
This wasn't going to cut it.
Not in the quantum world. And speaking of shaking things up...
Oh, yeah.
We can't forget Ernest Rutherford.
His cold foil experiment is legendary.
It's a classic. Talk about an experiment that completely upended our understanding of the atom.
It's such an elegant experiment, too.
Deceptively simple, but with mind-blowing implications.
Right. It's like something out of a first-year physics textbook, but the results were anything but textbook.
It's the perfect example of how science can surprise you.
So remind us what Rutherford actually did.
So picture this. You've got a thin sheet of gold foil.
Like thinner than aluminum foil.
Way thinner. We're talking crazy thin, almost transparent. And Rutherford fires these alpha particles at the foil.
And just a quick reminder for our listeners.
Good idea.
Alpha particles, they're basically helium atoms stripped down to their bare nuclei.
Like tiny little bullets of positive charge.
Right. So they fire these alpha particles at the gold foil. And the prevailing idea of the atom back then...
The plum pudding model.
Right. It sounds delicious.
But not very accurate.
It basically said that atoms were these positively charged blobs with little electrons embedded in them.
Like raisins in a pudding.
Exactly. So if the plum pudding model was right, those alpha particles...
They should have just zipped right through that gold foil.
Hit bullets through, well, pudding.
Maybe with a little bit of scattering here and there.
But for the most part, they should have gone straight through.
That's what everyone expected. But that's not what happened, was it?
Not even close. And this is the mind-blowing part.
Tell me.
Most of the alpha particles did go straight through the foil.
Which told them what?
That most of the atom is actually empty space.
It's mind-blowing when you think about it. If an atom were the size of a cathedral, the nucleus would be like a tiny little fly buzzing around inside.
It really makes you question what we mean by solid, but hold on.
There's more, isn't there?
That's not even the craziest part. A small fraction of those alpha particles, they bounced back.
Can you believe that?
That's like shooting a cannonball at tissue paper and having it bounce back and hit you in the face.
Rutherford was completely flabbergasted. He later said it was like firing a 15-inch shell at a piece of tissue paper and it coming back and hitting you.
That's an image that really drives home the point.
It really does. Those tiny little alpha particles bouncing off something supposedly much less dense, it was a revolution in the making.
So what did Rutherford make of these crazy results?
He realized that the plum pudding model had to go.
It was out the window.
Gone. And in its place, he proposed a radical new model of the atom.
One that could explain those bouncing alpha particles.
Exactly. He proposed that the atom must have a tiny, incredibly dense nucleus at its center.
Containing almost all of the atom's mass.
And that this nucleus was positively charged.
Which is why those alpha particles, also positively charged,
were repelled by the nucleus and bounced back. It was a stroke of genius.
So we've gone from this image of the atom as this mushy blob,
The plum pudding.
to this new picture where it's mostly empty space.
With this tiny, dense nucleus at the center.
And the electrons somewhere in that empty space.
Like planets orbiting the sun.
Problem solved, right. We've got our miniature solar system and everyone can go home happy.
If only it were that simple.
What do you mean?
Rutherford's model was a huge leap forward, but there was still a major problem lurking beneath the surface.
A quantum-sized fly in the ointment.
You could say that.
Yeah.
And this is where Niels Bohr steps in to save the day. It's like we replaced one head-scratcher with an even bigger one.
Right. So we've got these electrons whizzing around the nucleus.
With tiny little planets.
But they're also behaving like waves at the same time.
It's enough to make your head spin.
It's like trying to imagine a basketball spinning around a hoop, but also rippling outward like it was dropped in a pond. It makes no sense.
Our everyday intuition just doesn't cut it in the quantum world.
We need a whole new way of thinking.
And you know what's even wilder?
What's that?
At this point, physics throws us not one,
Oh, no.
but two completely different ways
Yeah.
of mathematically describing this whole wave-particle duality.
Two different theories.
Two different approaches to tackling the same problem.
Okay, I'm all ears. What were these two theories called?
On one side, we had matrix mechanics,
Okay.
championed by a real powerhouse trio. Werner Heisenberg, Max Born, and Pascal Jordan.
Those are some big names in physics.
They weren't messing around.
So what was the essence of matrix mechanics?
It was a pretty radical departure from classical physics.
How so?
It wasn't about trying to visualize things in a classical way.
With electrons orbiting a nucleus like tiny planets.
Exactly. Matrix mechanics was all about focusing on what you could actually observe and measure.
Like the energy levels of an electron?
Exactly. Things like position and momentum, those were a bit iffy in the quantum world, so they said, let's focus on what we can actually know.
I like their style.
They use these mathematical structures called matrices, which are basically grids of numbers.
Okay, so it's getting a little math heavy.
Just a tad.
Yeah.
But the important thing is that these matrices represented the different states of a quantum system.
So instead of trying to picture an electron orbiting the nucleus, they used these matrices to describe the probabilities of finding the electron at different energy levels.
Exactly. It was a really powerful approach.
But I'm guessing not very easy to visualize.
Even physicists back then were like, whoa, this is some next-level math.
So if matrix mechanics was the abstract, hardcore math approach,
It was.
what was the alternative?
On the other side, we had wave mechanics.
Okay.
And the champion of this theory was none other than Erwin Schrödinger.
Schrödinger. Didn't he come up with that whole cat-in-a-box thought experiment?
The one that still has people arguing about the nature of reality, that's the one.
I knew that name rang a bell.
He really leaned into that whole wave analogy we were talking about.
So instead of picturing electrons as particles orbiting the nucleus,
He described them as these waves.
probability waves.
Exactly. And these waves, they were spread out over space.
Like ripples on a pond.
Exactly. And the height of the wave at any given point represented the probability of finding the electron there.
So it's not that the electron was actually a wave.
Right.
It's that its behavior could be described mathematically as if it were a wave.
Precisely. And Schrödinger developed a wave equation to describe how these matter waves evolved over time.
And this wave equation, it actually worked. It made accurate predictions about how atoms behave.
It was a game changer. And compared to matrix mechanics, wave mechanics was a bit more intuitive, more visual. You could actually picture these waves spreading out, interfering with each other.
It's like those cool animations you see of waves interacting.
Exactly. Wave mechanics gave you that visual intuition that was missing from the more abstract matrix mechanics.
So we have these two radically different theories. Matrix mechanics, with its focus on observable quantities in abstract mathematics.
Right.
And wave mechanics, with its emphasis on wave-like behavior and visual intuition.
Two sides of the same quantum coin.
So which theory won out in the end?
That's the crazy part. Despite their completely different approaches, both theories ended up making the same predictions.
Are you serious? That's mind-blowing. So how did physicists decide which theory to use?
It often came down to personal preference, or which approach was more convenient for a particular problem. Some physicists found the elegance of matrix mechanics more appealing.
It's like choosing between a Ferrari and a Lamborghini.
Both are amazing machines. It just depends on your taste.
But it's still incredible that something as fundamental as the nature of reality could be described in these two completely different ways.
And that's the beauty of quantum physics. It keeps us guessing.
But all this talk about duality, of things being both wave-like and particle-like,
Yeah.
it begs the question, does any of this tell us what's really going on down at the quantum level?
That is the million-dollar question, isn't it? And this is where Werner Heisenberg, who, remember, was already a major player with matrix mechanics, drops another bombshell.
Okay, tell me more.
The uncertainty principle.
The uncertainty principle, that's one of the cornerstones of quantum physics, isn't it?
It's up there with the big ones, that's for sure.
But even I have to admit, it's always a bit of a brain twister.
It's a concept that really challenges our everyday intuition.
So how do we even begin to wrap our heads around the uncertainty principle?
Well, in a nutshell, Heisenberg showed that there's a fundamental limit to what we can know about a quantum object.
What do you mean? Like our instruments aren't good enough?
It's not just about our instruments. It's deeper than that. Heisenberg showed that the very act of measurement—
The act of trying to observe something.
Exactly. It actually affects the system you're measuring.
It's like the universe is saying, you can't spy on me without changing things.
That's a great way to put it. It's like the universe is playing a cosmic game of hide and seek.
So it's not about limitations in our technology. It's a fundamental limitation built into the fabric of the universe.
A fundamental fuzziness at the quantum level.
So give us an example. What does the uncertainty principle actually mean in practice?
Okay, so imagine you want to measure both the position and the momentum of an electron.
Momentum being like its speed and direction.
Right. Now, in classical physics, we could measure both of those things with pretty good accuracy.
No problem.
But in the quantum world,
Things get weird.
to measure the electron's position, we have to interact with it in some way, right? Like bouncing a photon off of it.
Okay, that makes sense.
But that interaction, that measurement, it actually changes the electron's momentum.
It's like trying to track a butterfly by throwing tennis balls at it.
You might figure out where it was.
But you're going to send it flying in a random direction.
Exactly. So the more precisely we try to pin down the electron's position,
The less we know about its momentum.
and vice versa.
So it's a trade-off.
Exactly. It's like the universe is saying you can know where a particle is or how fast it's going, but not both with perfect accuracy at the same time. It's a fundamental limit on what we can know.
It's almost as if the act of observation itself is creating the reality.
Or at least the reality that we can perceive.
Whoa, that's a mind-bending thought.
It really is. It's like the universe is a choose-your-own-adventure book.
And we get to decide which path to take just by looking at it.
It's a profound idea. And you know what's amazing?
What's that?
The uncertainty principle. It's not just some theoretical concept. It has real-world implications.
Like what?
It's the reason why we have things like lasers and transistors.
So the very technology that powers our modern world.
It's all thanks to this fundamental fuzziness built into the fabric of the universe.
That's incredible.
It really is. And it all goes back to those pioneers of quantum physics.
Planck, Einstein, Rutherford, Bohr, Heisenberg.
They took a giant leap into the unknown and came back with a whole new understanding of reality.
It's mind-blowing to think about how far we've come.
And we're still just scratching the surface.
It makes you wonder what other mysteries the quantum realm holds.
What other secrets are waiting to be uncovered?
That's the beauty of science. It's a never-ending journey of discovery. Well, folks, we've reached the end of our deep dive into the quantum revolution.
It's been quite a ride.
We've journeyed from the very first hints of something quantum in that pesky blackbody radiation to the mind-blowing realization that the act of observation itself might be woven into the fabric of reality.
We've covered a lot of ground.
But if there's one thing to take away from our exploration,
What's that?
it's that the quantum world is a place where the impossible becomes possible.
Where our everyday intuition goes out the window.
So the next time you find yourself questioning the nature of reality, remember those pioneers who dared to imagine a different kind of universe?
A universe stranger and more wonderful than we could have ever imagined.
And never stop asking questions because the quantum revolution is far from over.
It's an ongoing adventure.
And on that note, we'll see you next time for another deep dive into the mysteries of the universe.